Is Paul Olivella Rosell. I'm currently working in CITCEA-UPC at the Research Center, and also I'm a PhD candidate. And one of the topics of my thesis is about electric vehicles and the relation to their integration to the distribution grids. Why? So before to enter to the presentation, maybe explain you more or less how I decided to explain you the best or the most interesting issues about the integration of electric vehicles in power grids. So we have an introduction, basic introduction about electric vehicles. I don't know if you have a basic knowledge on electric vehicles. Have you discussed sometimes about the difference between hybrid, plug-in hybrids and battery? Silence means yes, silence means no. More or less? No? Yeah, but the other ones? Okay, so we're going to introduce you the basic concepts about electric vehicles. After that, we will distinguish between slow and fast charging, in which issues are different between one and another. So let's start with the introduction. Why electric vehicles? As this was introduced, we have an energy problem in the future. All the forecasts or predictions about energy consumption determine that the whole energy will increase in the scenarios without any big change, and most are increasing. We have the effect of fracking and also the OPEC effect, but normally is expected to increase in a basic scenario with a very big time frame due to the exhausted resource. Also, we have a climate change effect that we are now producing a bad effect on the ecosystem of the planet, so we need to reduce our pollutant emissions. And also we have, in terms of also geopolitics, the countries are interested to reduce their dependency on oil and fossil fuels and also gas. So it seems more or less logic that we need to investigate if we can change the current situation of the transport from the oil sources to the electricity sources. As Francisco also exposed, the share of renewables it's less than we could expect. And the reason to show you this figure here is because if we change all vehicles of the world to electric vehicles, but the production is from coal or natural gas, we'll have a worse problem with pollutant emissions. So, parallel with electric vehicles, we need to promote renewables in the system. Here you have a figure for countries about the current situation and expected situation in the future. And as you can see, Brazil and Canada are the most renewable countries in terms of electricity production, mainly due to hydropower. We should include Norway in the levels of Brazil, but the International Energy Agency maybe not include because it's a little country. But Norway it's equivalent to Brazil in terms of production. And in contrast, we have countries like Asia and China with a very few penetration of renewables, and is expected to be constant in the future because they plan to build nuclear power plants and coal power plants. So we have this scenario, and we will try to promote the electric vehicles. This figure is especially interesting to distinguish between different types of electric vehicles. The first one is the current vehicles with an internal combustion engine. This is the most extended electric vehicle is the hybrid electric vehicle without connection to the grid. This vehicle basic is using a transmission system coupled between the combustion engine and electric motor, and a little battery that tries to balance between the power, the torque from the combustion engine and the electric vehicle, to extract power during brakings and during the operation of the system, trying to operate at the optimal power point of the combustion engine, balancing with the battery and the electric motor. But the main source of these vehicles is still oil. In contrast of these basic structures, we have three proposals that it's expected to be operable in a few years. The first one maybe is the most known battery electric vehicles. This means that it's purely electric, there is no combustion engine, and all the energy comes from the grid. In parallel, we have an alternative with a fuel cell electric vehicles, where the main source is the hydrogen. They compete between which is the best model to be implemented in the system, and the reason of this competition is which grid has to be extended, mainly hydrogen grid or electric grid. This is the competition, and for the moment seems that the electric vehicle is on top of the competition, thanks to brands like Tesla and Nissan, which promoted a lot the brand of electric vehicles. But it's expected that the fuel cells will increase their efficiency and will reduce their cost enough to promote an electric and hydrogen electric vehicle. And we have a third alternative, which is the plug-in hybrid electric vehicle. It's like a medium term between the combustion engine and the pure electric vehicle. This vehicle has an autonomy expected to be between 40 and 60 kilometers. It's a smaller battery than the battery electric vehicle, but higher than the hybrid electric vehicle, and also the plug-in can be charged from the grid. It's between a medium term, and you can use both advantages from the oil and also from the electricity. You can move for your current displacements with the battery, and for your long trips during vacations, you can use also the combustion engine. This is one of the most promising also structures, but the drawback is that we still consume oil in the system.
What will be like the autonomy of that vehicle, considering both the electrical?
So you have to sum the autonomy from the combustion engine.
But I guess it's smaller, right?
It depends on the run. This is a decision of the run. There is no technical reason to reduce the gas tank.
You have a huge tank that also, the mass will increase, and so the electric performance will drop, right?
It depends. I think that this is not a problem. This is more related to the social expectancy about the vehicles, not a technical problem. I mean, you can increase both tanks, and the question is who will pay this vehicle. Do you know what I mean? If you increase, you can do a vehicle with an autonomy higher than 1,000 kilometers. But the problem is who will pay this battery. Okay. So the autonomy expected of these vehicles is more or less 1,000 kilometers, because you have the electric vehicle, the electric motor, and also the gas tank. But in case of the plug-in hybrid, the autonomy is not the question. It's the cost of both motors, because you have you have to pay the battery, the electric vehicle, the electric motor, and also the combustion engine. And also you have losses between the transmission power between combustion and electric motor. So normally these models are expensive than purely electric vehicles, but it depends. Tesla is expensive than Mitsubishi. For example, the start of this structure is Mitsubishi Outlander plug-in hybrid electric vehicle Outlander, and this vehicle has been sent a lot in UK, where there is a huge incentive public to promote these kind of vehicles because they have both. But Tesla Model S, it's around $80,000. So it depends on the case. Tesla is a luxury car, and Mitsubishi it's a very good car, but it's not luxury. Okay. Okay. Here you have a general figure about benefits and drawbacks of each structure. I would like to highlight mainly the challenge of electric vehicles, which, as you expect, is the autonomy and the range of the vehicle, which is lower than 250 kilometers. And the benefits or the performance of the combustion engine is the high driving range due to the efficiency, not efficiency, sorry, the power in oil. So the problem here is that the expectancy of drivers is to have a vehicle with a lot of capacity to reach any destination. So it's not possible to avoid a comparison between the combustion engine and the electric vehicle. So if we compare, we will say, okay, electric vehicles are not enough developed for the moment. But the question, from my point of view, is not this. The question is purely if the electric vehicle will be enough for me, for my current displacements. Okay? We will talk about this, about the distances and the range in slides later, but just remember this question. Is this vehicle good enough for me? Not if it's better or not of the combustion engine. Okay? Something to be highlighted from this figure also, the medium term of the plug-in hybrid electric vehicle, which have a huge range of battery electric vehicles and less emissions, but is still consuming oil, so this is not a long-term solution. And also highlight the drawbacks of fuel cell and electric vehicles are the current cost, that it's higher than people can pay for this performance. So normally the people who are buying electric vehicles are people who are are people with a high salary, with high economic capacity, and also are people who are worried about the environment and the possibility to avoid greenhouse gases emissions. This is more or less what is expected. I've seen a lot of these figures with different possibilities. I think that this is one, and it's good. It's not possible. In fact, it's very difficult to think that in the next 15 years we will have a very huge revolution, avoiding all the vehicles from combustion. So it's not real, but we are expecting an important development of these vehicles. This figure will depend a lot in two variables, in my point of view. The first one is the oil price. If a tank costs more than 200 euros, anyone will pay this. They will reduce the expectancy about the range and will buy an electric vehicle. And also the second parameter that need to be considered in this figure and which will change everything is the lithium exploration and the battery technology. If we get a battery which is capable to, with an acceptable economic cost, do 500 kilometers and to be charged in 30 or 40 minutes more or less, everything will change. So we will see what happens in the future. So what will be the real situation? Many questions need answering. I'm absolutely in this direction. So the first one, how many plug-in vehicles will be there? The second one, what will these vehicles be like? How much energy will they need? How far will they be driving? So we have this question regarding the electric vehicle. So, and the second question, which is focused on this presentation, is how we will charge this amount of vehicles connected to the grid. So, what charging facilities will exist, when and how will charging take place, and also the transmission system and distribution, how can local overload be avoided, and also the generation, which is, has a limited capacitor, and also the emissions of the system. So mainly we will focus on this question. Just to be explained, there are two kinds of charging possibility of the electric vehicles. The first one is the slow charge in 3.5, 3.6 kilowatts, which means that you need approximately 8 hours to charge completely your battery from 0 to 100%. And the second one is the fast charging, which is designed thinking about the long distances when your capacity, battery capacity is not enough to reach a huge long travel, and you need a medium-term charge between your displacement. So you cannot wait 8 hours to continue your trip. So the fast charging solution is a 50 kilowatt solution in direct current directly to the battery, which can charge your battery in 30 minutes, more or less until 80% of the battery. So we have two solutions how to charge the electric vehicle, the slow and the fast, and we will see which effects will produce on the grid each one. Here you have a typical day in UK, in the grid, and the question is, what happens if every one of us reaching our home at the end of the day, connect all the vehicles after a long day driving for long distances, and all of us expect to charge when altogether wants the energy. The result will be an absolute overload in the system, which will produce a huge peak, and this huge peak means new generation, also from fossil fuels, because we need to be produced for sure at this moment. So we need fossil fuels to produce this peak, and also we need an grid upgrade to permit this peak at this moment. So if we don't do anything with the charging of electric vehicles in a massive scenario where every one of us who have an electric vehicle will charge at the end of the displacement, we will produce a peak, and this peak will cost a lot in grid expansion and also in terms of generation. So what we can do? The solution proposed is, in general terms, smart grids. Smart grids are the technologies which enables to control the consumption in houses with the best way. In this, in smart grids are more than this, but we are focused on the control of the electric vehicles charging to be charged at the best way. At the best moment when, for example, we have a surplus of renewable electricity. So the question is, how can we manage these vehicles in the system? I would like to highlight the importance of communications technologies, which enables the possibility to have different sensors in the grid to send messages between managers and electric vehicles, and everything it's automatic. Because, for example, if you think in the future that when you will have an electric vehicle and if we don't have any way to communicate with the distribution system operator, will tell you when you can charge at the best prices, or with your retail company, which will offer you the best offers with the cheapest energy to charge your vehicle. If we don't have communications, everything of this cannot be implemented. So the importance of communications is very important. So what we have here, 3 possible scenarios of charging. As I mentioned, the first one is with a peak in the system, increasing the capacity of the grid, the capacity of the generation system, and probably the sources of this generation, of this energy will be not renewable because the vehicles cannot be managed. The second option is thanks to a possibility to distinguish between the prices in each moment. I mean, if every one of us have a different electricity tariff in which at the first hour of the day we have a discount of 50%, every one of us will install a clock to the plug and will program it to be displaced the consumption at the hour the cheapest way. But the problem is that everyone will do the same, and we will create a peak during the night, promoting that this energy needs to be produced also from oil and gas, because everyone will connect at the same moment, and we will need a control to maintain the stability of the grid. We will need fossil fuels to produce this electricity. So, to displace the curve to the valley period, it's not an easy solution. We need control to manage this vehicle, to reduce the power consumed to the grid, and also to coordinate renewables and electric vehicle charges. This is the typical profile of electric vehicles in terms of the slow charging and the fast charging profile. As you can see here, this is a continuous line between 0% and 93%, at which the vehicle is charged at the nominal power of the charge, 3.3 kilowatts, and after 93%, more or less, the power is reduced to extend the life of the battery. But a similar thing happens with the fast charging, which at the beginning of the charge, the power is at the maximum, 48 kilowatts in the system, and to extend the lifetime is reduced to avoid overcurrents in the cell system of the battery. So we have 2 alternatives to charge the vehicle. In fact, there's a curiosity. Nissan Leaf, which is a model from Nissan, at the beginning of the expansion and selling electric vehicles, some users only choose the fast charging profile to charge the vehicle. What happened? 2 years after the first day, the battery was lost more or less 20% of its capacity due to this use of fast charging. And the users and the owners of the vehicles said to Nissan, hey, in the warranty, there is no limitation of fast charging, and you ensure me that I will have more than 80% of the initial capacity for more than 2 years. So, what's happening here? Nissan replaced the batteries, as the guarantee said, but at the next day, the new guarantee for no-use sleeve included the maximum use of fast charging in this of the battery to maintain the guarantee. I mean, I don't remember exactly the number, but I think that there are lower than 100 fast chargers to maintain the guarantee of Nissan. So here we have a clear example about what's happening about the knowledge of the companies and the battery life expectancy.
In the illustrated graph, what is the second line in the negative?
The second line is the reactive power consumed. Okay? Okay. We will recover the question that we had at the beginning. Is this electric vehicle enough for me? The answer of this is related to the normal distances traveled by vehicles. Here you have a figure which is represented the probability and the distance, and it means and different countries, and it means that 40% of displacements in Italy are lower than 50 kilometers, and the general number that you have to remember when someone asks you about which is the average distance in Europe is that more or less 80% of displacements will be lower than 80 kilometers. So, based on that, we can do more than enough with current electric vehicles because 80% of displacements are lower than 80 kilometers. So, the question is why users are not buying electric vehicles a lot. The question is, the data that is not in this figure is that for 2 or 3 displacements of the year when some people goes far away with its vehicle for holidays, the electric vehicle will not be enough for the expectancy. So, based on 2 or 3 days every year, people are saying, and it's completely comprehensible, people need this vehicle for these days and they don't think that it's good enough for them. This is curious, but this is people. Yeah, and if I would like to buy a vehicle, probably will do exactly the same. But it seems not logical in terms of logic decision.
But it's also the price of the electric vehicle.
Yeah, but you will recover.
They're not.
Think that a displacement of 100 kilometers will cost you less than €1 in electric vehicle.
Yes, a long-term investment it might be, but short-term, not so many people can afford an electric vehicle.
Yeah, of course, but I'm completely sure that the people who can afford this inversion is not thinking about if it's cheapest or not. They are thinking about
That's true.
their travels that are higher than 1,000 kilometers. This is not logical, but it's happening. And, well, the second question that I would like to mention you is that when the electric vehicles will be charged. If we expect that the people will use at the same way combustion engines and electric vehicles, we can think that the displacements will be focused between the morning, when people are going to office or to the university or what else, and after, at the evening, when people go back home. So, if we produce a system in which people arrive to its destination and connect the vehicle, we will have the corresponding peaks in the energy consumption, okay, as we will see later. So this is a very important variable which can explain when electric vehicles will be charged. And we'll have a lot of time, and I don't want to spend in this figure. Basically, I would like to try to emphasize that there is a direct relation between the electric vehicles usage and the charging needs for the system. So we need to include mobility variables in the models that try to predict when electric vehicles will be charged and the corresponding effect on the grid. So this is the algorithm that can be used, including mobility patterns, including EV characteristics, because it's not the same to charge a Tesla and a smart electric, and also the charging process and the decision of the owner, which decides between a fast charge and also a slow charge. Okay, and there is an interesting question here, because how can we manage these variables? Because many of them are absolutely random. Absolutely. When do you open the lights? Whenever you want. And if you try to model a variable how people open, or when people open the lights, it's probably absolutely random distribution, which is very with a lot of variation. Mobility and the charging process has a similar behavior, because you will reach your destination with a few time deviations, because maybe one day go to the cinema, or one day go to the shop, or one day go to the dinner. So we have a lot of variability, and this variability will be translated directly to the charging profiles. So this is a problem, and we have to manage this problem in a probabilistic way, with probabilistic variables. So you can see here the number of travels per day will be a probabilistic variable. The total distance also will be a probabilistic. EV model can be also probabilistic, because there is no standard model for all. We have different models, and also the time distribution, as I mentioned, is a probabilistic variable. So there is techniques which allows engineers to deal with these problems with a lot of variability and stochastic variables, which means Monte Carlo methodology, which in a general idea is a methodology to implement in probabilistic inputs and to get probabilistic outputs to be analyzed statistically. Okay, this is more or less general idea, it's not the focus of today. And to see the problem, we will talk about a specific case study, which is a general idea about how a distribution grid is. More or less, here you have a distribution line with 37 nodes. This is the typical topology in IEEE, 11 kilovolts, and this is supposed to be an old line in a medium of the city with a lot of consumption connected to it, and the question is, can this line charge the vehicles of the owners which are connected to this grid? And this is the question that all electric companies will have to solve in the future, because they have a lot of lines and will have different population distributions, and probably the owners which are now connected to these grids will need a charge of the system. And the question is, can these lines charge these vehicles? And can we avoid an upgrade of the lines, because this could be very expensive. The line and the network is a very expensive infrastructure. So we need to install technologies to avoid a massive expansion of the system. This is the initial situation without electric vehicles. You can see the profile of the worst day of the system, located in winter, and with a peak at the evening. As I mentioned, this line is near to its maximum capacity. These bars are the maximum current reached in this profile, and as you can see here, there are 36 lines, and also there are a few of them near to its capacity. So the question is, can this line charge the electric vehicles? And also, because it's important always to analyze the voltage at the end of the line, because there's a maximum voltage drop permitted in terms of operation of the network, and also it's an important variable. So as you can see here, this is the case that we want to analyze. We defined 6 groups of EV users, 3 private and 3 professional. 3 locations, local, which means that are directly connected to the grid. Their households is connected to the grid. Local, urban are vehicles which are from the same city and pass through the line. So it means that probably between displacements they will need a charge to continue their day. And also metropolitan, which means there are people from other places which arrive to the city, and probably after a long displacement they will need a charge to reach back to home after the day. And we designed 4 scenarios. An intensive one, which at the end of its displacement people will need to charge because they have a lot of anxiety about the range of its vehicle. And also plug and play, which is at the end of the day we play because the electricity is cheaper at home. And also we'll compare to time of use tariff, which I don't know if you know which time of use tariff. It's mainly that the electricity is different for different electricity price is different in different periods, and we will compare the tariff controlled, which means that there is an hour when electricity is cheaper, and also compare the scenario with an aggregator which can control all the EV fleet. The first result is that the first scenario is this one, which we can see, as I previously mentioned, that the people will charge at when they reach the office during the midday, and also the energy consumed at the evening when they go back home. So this consumption can be translated to the main to the total amount of power consumed of the grid, and you can see that this is not a significant increase. This is between near 11 to more than 11 megawatts. So this is not real in terms of power. It's not a big challenge. But the problem is that the black boxes of this means the difference between without electric vehicles and with electric vehicles. And as you can see, this peak increases the maximum saturation of the lines, and then you can see that the line, in fact, cannot cannot charge these vehicles without changing the sections of these lines. In terms of voltage, there is a big huge, because the minimum voltage permitted is 0.93 P per unit. So in terms of voltage, there is no problem. But in terms of line saturations, there is problems. If we change the scenario and everyone try to charge at home, you can see here that the peak at the evening will increase a lot because there is no consumption. The batteries at this point will reach the destination at lower capacity. But this peak will increase, and also the peak in the total demand will increase, and the saturation will increase. This scenario is curious because, as I mentioned, if everyone tries to charge their vehicle at the same moment, we will produce a peak on the system, which is not a problem in terms of the system, of the distribution system, but will be a problem to the operation and the generation system, because we will need thermal generators ready to produce at the moment when all electric vehicles try to connect the vehicle. So this is not a solution, and also this peak, this consumption here will increase the line saturation. The solution expected to be in the future is this one, where there is an aggregator which manages the electric vehicle consumption to be displaced completely to the value period. And this way, as we don't have any consumption in these periods, we don't have any effects from the grid. We don't have enough time. this is more or less more results, but the general idea is well explained here. What can be done in an advanced way? Vehicle to grid. If we can operate the vehicles connected, charging and discharging the vehicle when the system needs this energy, the operation of the system will be easier. For example, in the United States, Mr. Kenton has studied which is the possible benefits or income from a vehicle to grid charger, and he expected and them argued that an EV owner with a bidirectional charger of 18 kilowatts can receive near $2,000 per year due to two services. The first one is the capacity in terms of power, because the vehicle can pass from 0 to 18 kilowatts in terms of seconds. So if we have a huge fleet of with bidirectional chargers, we can manage a lot of deviations in the system. And also in terms of energy, because there will be a few hours where the system will need your energy. So there is a lot to be studied here. As you can see here, here in CITCEA we designed and implemented a bidirectional charging station with 6 bidirectional chargers, and they have been installed in the smart city of Malaga in collaboration with Endesa, which now operating this charging station. And the results of this project will tell us which is the real benefit of this possible service in a real situation, a real pilot, because Malaga has a lot of vehicles driving in the city, and we will see which is the real, and also if the EV owners are interested to discharge or to receive a little bit economic compensation for this kind of services. There is, I will finish here. There are 3 different hierarchical architectures of EV management. The first one is the centralized, which there is a controller which manages all the fleets in a distribution line or a distribution area or wherever. There is only one who take the decision. And also there is an alternative of this, in a hierarchical control architecture, which have mid-term agents who are aggregating different little fleets with different proposals, and there is a control center which talks about with the DSO and the TSO. And also there is a distributed control architecture, which means there are negotiation. Probably, as Guillem told you in the previous presentation, there is a potential micro-markets creation between the negotiation between EV owners and producers and consumers to charge the vehicles at the best moment of the system. I'm sorry, but there is no time for the last part of the presentation. I think that the problem capacity of the system is higher, and if we install 3 fast chargers in the line, we will see a lot of variability in the system, which means that the power consumed of these 3 chargers will compromise the operation of the whole line, because there is a huge capacity of these chargers. So the fast charging integration is a problem, very specific, but it's has to be dealt in the future. What's next? Storage integration in the smart homes, aggregator algorithm to manage these EV clusters, and also market participation to have the cheapest energy consumption to charge the electric vehicles. Also to integrate vehicle-to-grid capability and new business models where there is a potential benefit controlling the EV charge in the system. And that's all for me. If you have any questions, if not.